Hi, sir. Hello, 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 hello. Do you hear me?
Yes, I do hear you. Tell me.
Hello, bro.
Hello.
Hi, 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 sir.
Hi. What happened?
Nothing, sir.
Yeah, we'll start the class in 5 minutes. I'm waiting for others to join if in case someone wants to.
Okay, sir. Sure.
Okay, so good morning. I hope you can hear me. Yeah. So we only have one student right now. I guess more will join in a few minutes. So, but we'll start. So today, it's the last doubt clearing session for it's because it's the last week, so week 12. and we'll discuss today demonstrations and so uh, we'll continue with what we were discussing last week. We left off with DC microgrid, and now today we'll discuss how can we demonstrate a DC microgrid. So demonstration and all, I figure if you can, I mean, I won't be going in depth because there's no concepts involved, but at all places where there are concepts, I will try and engage you. But in case, but you have to watch the week 12 lectures available on NPTEL for because they demonstration is something that I can't show you because I am not familiar with that kind of uh, setup. Okay. And so today we'll discuss, it's the last week. So from since week one, we discussed everything related to smart grids. So we started off with why smart grids are required. Then we moved on to how smarter grids are becoming into, coming into picture with the smarter equipment like PMUs or micro PMUs, and then other relevant stuff. Then we also discussed some of the protective relaying and then microgrid structures. And from the last few weeks, we are currently discussing about demonstrations of these microgrid structures, which are just representation or simulation of your of all the mathematics. I won't call it mathematics, of all the concepts that you have learned so far. Uh, this week 12 is also there's no surprises. We have demonstrations only, and uh, um, we'll discuss that only. So let's let me share my screen. Okay, it's yes. Okay. So so how does a DC microgrid look? What is the basic difference between a DC microgrid and an AC microgrid? It's just that for a DC microgrid, for DC loads and DC generation side, we have a DC bus in place as well. And this DC bus, we generally, the microgrid is configured to work, coexistent. It's configured to coexist with the main grid, which is generally an AC grid. And in similar scenarios, what we have shown here is a DC microgrid. Increase the size of it. Yeah. So we have here a DC microgrid, which is uh, which is connected to yeah, which is connected to this main grid, which is nothing but your, yeah, it's a synergia based. You can call it a utility scale synthetic power generating device. So it doesn't do anything apart from the fact that it can simulate grid conditions. That is, it can simulate how in real time a utility grid uh, um, grid would look like. So in IT Roorkee, they have this synergia based uh, 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 synergia based equipment, but in IT Kanpur we have a Chroma based microgrid. We call it an AC microgrid, but we can configure the peak voltage and peak current that we can take out from that equipment. So it's connected to the PCC. So PCC is the point of common coupling where you connect your DC bus as well as your AC loads. And this DC bus is configured using this AC DC converter, which has a DC link. And DC link, we all know why is it required. It's required just in case if there are irregularities in your AC side. The DC side should have a smooth voltage across its power points. And then it's configured. The DC microgrid is configured in Opal RT. Last few weeks, we also discussed what is a real-time simulating device. I hope you all are familiar with what a real-time simulator is. A real-time simulator is just your normal simulator. It's just that what it does is it syncs all of your control signals, your signals coming out of your system or into your system with real time. So that let's say that you simulated something on MATLAB, right? So in the bar below where it simulates stuff, that bar shows in seconds or minutes, whatever it shows. It's not figured or configured with your universal time, right? It doesn't show that it's giving you perfect output. Like for example, it can simulate in milliseconds, but it's supposed to give output in seconds, right? So, I said, so it simulates in seconds, but it's supposed to give output in milliseconds. Let's say that you want to trip a relay. The relay should be tripped fast enough, right? It's required in milliseconds. If the simulation shows 5 seconds, how will you test it in real scenarios, right? So for that, what you need is a real-time simulator. So Opal RT, RTDS, and then you have Typhoon HIL. All of them are real-time simulators, and what they do is they are configured with a GPS, which then makes sure all of your simulations are simulated in real time, so that if your trip if your relay trips in milliseconds, it will trip in milliseconds in real life as well. So so all of this DC microgrid along with the DC load is configured in Opal RT, which is a simulator. And to take out voltages and current input to that, we are feeding it through analog input output cards. So I don't know about Opal RT. I really haven't worked with it, but in RTDS we refer to them as GTAI or GTAO cards, which are gigabit transceivers analog input and gigabit transceivers analog output. So I hope these are also gigabit transceivers, but if they have written AIAO, I'll just say that they are analog input pins and analog output pins. So what's the fun of analog input pins? Your voltages, which are in time domain, these are your analog signals. And what you really want is before inputting them to your simulator. So your RTDS, even though it shows simulations in time scale, but it won't be familiar with analog signals, right? Before, after this step, sorry, after this step, there is an A by D converter, which is it converts it to a digital signal so that it can be recognized by your real-time simulator as well. So that's the basic overview. And then your DC bus has PV and battery energy storage systems and some DC loads. So all of them are being simulated in real-time simulator. And for your DC AC converter, AC DC converter, which is at the forefront, this converter, its control signals are being issued by a digital signal processing board, which takes into account the utilities voltages, which is ABC parameters of all the three phases, the current, and your DC link voltage. So to be able to correctly configure the PWM of your AC/DC inverters, you need all of these three variables. The inner control loop is similar to that we discussed last week. So I would request you, if you haven't watched the last week lecture, you can feel free to watch them on YouTube. So the control logic is similar, and the output is your control pulses for your six switches, which are your AC to DC converter switches. So in this, what really happens is what you want to do is you want to focus on energy management between your DC side and your AC side. So you have DC loads, you have DC generations, your PV or BESS, and you want to make sure that they are being properly managed through their utility grid as well. So let's say that what really happens is your utility goes into an outage, let's say that, and your DC microgrid starts working in isolated mode, right? So if that happens, then the DC microgrid should know that the AC microgrid is no more there, and proper energy management functions should kick in so that your DC microgrid could survive on its own. It won't require the help of your AC uh, system. And for this, a proper energy management scheme that we have been discussing for the past few weeks needs to be derived appropriately. And for this, the instructor has shown you some test cases which have these uh, energy management scenarios where what happens if your PV goes out or your AC grid is not available to you. And your DC bus, the voltage at your DC bus this voltage is always regulated. I mean, if I say it's regulated, it shouldn't change much, and it's being regulated through this interfacing converter. This is called an IFC or an interfacing converter. Right. So that's just how your DC microgrid in conjunction with your AC microgrid works. And I would ask you to go through the video where they have shown you how the individual stuff looks like, the converters, the outputs on the CROs, and you will be able to better gauge how. So the idea of this demonstration is basically to make yourself feel comfortable with how, let's say that you devise a successful technique, right? You devise how to control your interfacing converter. Now you want to check it out. How will you do it? You have to, you can't be like, okay, I'll create a microgrid. I'll connect it with my AC grid, and then I'll check if everything is behaving as is required. No, for that, what you do is you simulate on real scenarios. And how do you do that? It's through this uh, power hardware in loop demonstration. That's what it's for. It's the stage before you deploy your equipments in field. So that's what it's required. Now, the next thing that the instructor discussed was your PHIL experimentation. So for this PHIL experimentation, again, it's the same thing. So all they are doing is they're demonstrating a few scenarios so that you are comfortable with how these uh, the simulations happen in real time. So for a PHIL, I'm just explaining this again. I have explained this, I guess, in week 10 lecture as well, how a PHIL experimentation works, but I'll do it again. So you have an RSCAD software. So RTDS, your real-time digital simulator, comes in with an RSCAD, which is like a MATLAB for this RTDS. So this RSCAD is the simulation software for your RTDS. And what exactly it does is, let's say that you have a DFIG and you want to test out some things in this DFIG, right? So what you do is you run this DFIG along with your grid, then you output its current or voltage. Now this current or voltage are inputted to your RSCAD using a GTAI card. Now your GTAI card accepts these sensor currents, but can feed the RSCAD only in this range, plus minus 10 volts. So for that, what you do is you filter it and then you give it to this RSCAD simulator. And to take out output from it, what you do is it gives you results in digital domain, right? So this digital domain needs to be converted to analog domain using an A by D or D by A or digital to analog converter. After that, this digital to analog converter converts this digital signal, because since it's a computer, right, the output would always be digital. And this digital to analog converter will figure it out to analog. But then this analog is in plus minus 10-volt domain. You scale it and then feed this output back to your power amplifier. And this power amplifier is nothing but your main grid, right? The one that you're simulating on. And then this whole feedback happens between the rest of the equipment. So all in all, so this is why it's called power hardware in loop, right? You're giving it input, taking the feedback as the output, and feeding it to your original power converters or power systems and power devices. And based on their feedback, you're feeding back the results back to the simulation software. Now, this helps you in demonstrating that your product is ready for field deployment, and that is something that is this pass is something is required for you to be able to say, okay, if you have configured a control logic and that control logic works perfectly on your MATLAB, that's not enough proof. You need to show that it would work in real time as well. And for this PHIL or controller hardware in loop simulations come into play. Now, in this exact demonstration, what the instructor's idea was that he simulated a DFIG in a power hardware in loop simulation platform, and he wanted to check what is the transient analysis of its of this setup two symmetrical and asymmetrical faults. So what are symmetrical and asymmetrical faults? So as the name suggests, so these are the faults that happen alike in your all three phases. So your three-phase to line or three-phase to ground fault. Three-phase to ground fault is something. Three-phase to ground fault, and your asymmetrical fault is which happens independent of your phases, like one phase to ground fault or two between two phases, etc., etc. Just writing an example. So based off on that, what the instructor is simulating is that he has this he has this setup. This is a single eye diagram of the whole situation. There is this utility grid which is taking power from this power amplifier, and you have some grid impedance which can also be simulated in this power amplifier. Everything. So this power amplifier can be used. I mean, I don't know about Synergia that they use, but a chroma base that is present in IIT Kanpur, you can configure everything starting from your control variables and your peak voltage and current scenario. So on this second bus, which is connected to a transformer, which converts 480 volts to 480, yeah, 480 volts to 11 kilovolts, and this transformer is connected to this bus too, which is experiencing these two kinds of faults. So what exactly the instructor wants to talk about is that if a DFIG is connected to this third bus, how will it respond to this faults? So what they want to do is they want to formulate a transient analysis of this DFIG. Now to simulate this, what they have done is, okay, they have connected this DFIG to this power amplifier, which is in turn connected using this GTAO card where this whole network is being simulated on RTDS. So this GTAO, which is gigabit transceiver analog output card, sorry, analog input card is where you want to input your stuff, is taken into your RS card and it gives you results and it's fed back to this GTAO card. And this DFIG is simple, so you want to simulate real wind scenarios, right? Now what you would do is you would say, okay, I need a new wind turbine or a wind plant or a windmill to be able to simulate these. So that's not something that you do in at least in labs. So in laboratories, what you have is you have a wind characteristic emulation tool. Now what does it do is you connect your AC supply, which is then converted. So AC is first converted to a DC. Sorry, which is then connected to a DC motor, and this DC motor is connected to a chopper. And in this chopper, the switches are simulated according to this wind characteristic simulation tool. Now, based on this, the turbine is rotated using this prime mover from DC motor, and it simulates it rotates this DFIG, which is a double fed induction generator. Why it's called double fed induction generator? It's because apart from having connections on stator grid, the double fed the induction generator also has connections on the rotor side, and it's necessary because let's say you have variable power at your um, this you have variable power at your prime mover, but the output of your this DFIG should be figured out in such a way that frequency is maintained. So the frequency shouldn't be altered just because your this prime mover is behaving in a different way, erratic way. Your frequency shouldn't be compromised. And for that, what you do is you take power from your stator when required so that the necessary slip could be issued by moving the rotor fast enough by using this rotor side converter, which takes power from the stator side. And if this prime mover starts uh, taking more power, if this prime mover starts rotating the DFIG to a very high extent, then it feeds power back to this system by using this rotor side converter. So both of these converters are your bidirectional converters. So I've discussed this in, I guess, I don't remember, week 10, week 8, I guess. Just looking, week 9. Yeah. So same thing I discussed in week 9. So what happens is based on how your prime mover is taking in energy, see it's simulated for high power, low power, etc. etc. It's making sure that the output from the DFIG remains constant. So this P stator is constant. How? By making sure that you are taking necessary power from this utility grid. So that the utility, even though gets low power, your frequency is not compromised. So by using this illustration, you would be better able to understand this concept. So that's the whole idea of DFIG. Now, in order to control this, you have two converters, your rotor side converters and your grid side converters, right? And to control these converters, you again require uh, control algorithms for each of these converters. And for that, what you do is you take into account your rotor side and grid side currents and your rotor side, your grid side voltages and your rotor side, the frequency of rotation. And based on that, you calculate the phase angles at which your switches will rotate so that bidirectional power flow could be maintained in a way that would suit the whole overall operation of your design. So after that, what it does is it's connected to this power amplifier, which is then simulated using this RTDS racks using GTO and GTI pins, which is and in the RSCAD software, your network is being maintained. So the analysis is to is to check how your DFIG would react to your three-phase to ground faults and one-phase to ground fault. And in the instructor's video, at the if you have watched it, I hope you have watched it. I mean, it's the last week, so your exams are very close. In that he has shown how a DFIG looks. I mean, you must have checked, and how the output at the CRO looks like. So at each instant of the fault that takes place. So basically, what you want to check is how are your transients behaving when your faults occur. Now, now the next thing that the instructor focused on was ancillary service support from VSG. Now, what is a VSG? It's virtual synchronous generator, and sorry, virtual synchronous generator. And the main idea of it too is to uh, act as a synchronous generator. Now, why do you want it to act as a synchronous generator? It's because by the use of these intermittent resources, uh, this this highly intermittent resources, and your BESS and other equipments, your inertia of the system goes down by a very high margin. Now, this inertia, you all know, it's very important to make sure that your frequency doesn't dip. If let's say something happens, if there's a loss of generation, too much loss of generation, and the frequency starts dipping. So when this generation loss happens, what happens is the frequency dips. So I'll just show. So let's say that this is your 50 hertz frequency. So what happens is, let's say the frequency was working fine. It was like 50 hertz up and down. But then as soon as, let's say, PGen loss happens, the frequency starts dipping. Now to control this dip, what happens is each of the synchronous generator has some kind of inertia in it. I mean, it's a rotating body, right? So if a rotating body is there, if the motion of the rotating body is halted, it continues rotating for a few seconds. Due to that, what happens is, let's say there is a huge generation loss, the power from the existing generators continues to be the same for just some seconds. So, I mean, so not some seconds, some milliseconds. Now, the use of this is that it controls the rate of decay or the ROCOF, rate of change of frequency, to a certain extent. So this is called frequency nadir. And frequency nadir is the lowest point of frequency after some irregular scenario takes place, right? Now, all of this is contained by the inertia of the system. Now, let's say that you don't have any inertia in your system, right? You're using all power electronic equipments which have PVs, this, BSS, etc., etc. So there is no inertia, right? And to control that, you need to have some kind of a virtual synchronous generator, and it's called virtual because again, it's still a power electronic device, but it's controlled in such a way that it acts or mimics the properties of a synchronous generator. So, so the instructor took the case of IIT Roorkee's distribution system. So in IIT Roorkee, what they have is need. Okay, I'll do one thing. Okay. Hmm. Yeah. Okay, so this is the IIT Roorkee's distribution system. So what they have is they have a lot of PV. I mean, it's a campus, right? Like in our IIT Kanpur's campus. So there are a lot of PVs installed, rooftop PVs installed in all of the hostels. So all hostels have PVs. So there also the IIT Roorkee's campus, all of these hostels and apartments or buildings, whatever they have a lot of PVs, as you can see. And these A, B, C, D, and E are your BESS or your battery locations, and they have two diesel generators as well. So this diesel generators uses when this IIT Roorkee's distribution system, which is also a microgrid now because it has generation available. If it is islanded, so that these diesel generators are energized so that the bus here, the point of common coupling, can have this 11 kilowatt of energy ready. So, so the diesel generators, they are used only when energized islanded operation, right? And then you have so basically due to all of these equipments, their percentage of power coming from these resources is 45%. So due to this, what really happens is their inertia is significantly low. Okay. And now for this, what they did was, let's say if the inertia is significantly low, what they want is how to increase this inertia, how to get virtual inertia into the system, in the system. So this virtual inertia could be from your virtual synchronous generators. And this virtual synchronous generator is something that they propose as uh, this VSG is something that they propose as a grid supporting unit. That is, it supports grid, and they have a total of, I guess, 2.5 megawatt capacity, right? So their 2.5 is 2.5 megawatt capacity is taken from for this VSG, and they have a lot of load. And generally, since it's a campus building, right? It's a campus building. The loads are very irregular. Let's say that during summers, peak summers, you have summer vacations. So during summer vacations, all of the hostels are vacated. I mean, not PhDs or masters, but UGs generally vacate their hostels, due to which there is a large amount of load which leaves the system. But they have this whole wide array of PVs, right? And they can't just switch it off. And they are in contract by providing this power to different places as well. So what they do is they use some energy management schemes to be able to better manage the whole infrastructure. Will come into that, and for that, this battery energy storage system is something that they use. We'll come into that, but I just wanted to tell you this. So again, for this, what they did was they had a PHIL implementation, which is a power hardware in loop implementation. In your RTDS or RSCAD software, they simulated the distribution system of IIT Roorkee, and their their power amplifier, which is the one that acts or mimics your AC side or your utility side. So what exactly is, it's a 33 by 11 kV utility, right? So it's supplying power at 33 kilovolt, and after that there are transformers which convert it to 11 kilovolt. So they are simulating directly at 11 kilovolt, 550 hertz three phase power. And what they have is they have a wide array of switches. Now, what exactly is the need of them? Let's talk about this. Now, all of this power coming from these three sides or three legs, we should say, it's being fed to this filter, which is a ABC filter, right? VABC. Now, in this ABC side, what they do is it's a 200 plus and minus range of voltage that they are supplying. So first of all, what they do is they use a phase lock loop converter. What's the use of phase lock loop converter is that any reference that you want to create should be in phase um, with your utility phase, right? If it's out of phase or out of sync, what really happens is your control algorithms won't mimic the kind of control you want to have for the system. So for that, you need to have a phase lock loop. After that, they have an active power loop and a reactive power loop. An active power loop takes in uh, the the frequency and reference frequency, and the reactive power loop takes in the reference voltage. So we all know why, because the correlation between reactive power and voltage and active power and frequency. And after that, they have, I won't go into detail, but they have these three control algorithms. Now, what exactly these three control algorithms do is that these are used to mimic your swing equations. Now, does anyone have an idea what a swing equation is? Anyone who knows what a swing equation is? No one. Okay. So your swing equations are the ones that these are second order equation. Oh, I won't shouldn't say equations. I mean, there are two equations, but I mean, they're just constant value. I'll just talk about it. Second order equation, which relates frequency with power. So what exactly these look like is something like this. Right. So all of them are so what exactly this equation does is it relates how your mechanical input and your electromagnetic. Okay, so some part of your to maintain the frequency, your synchronous generator takes in some mechanical input, out of which some is used as for developing that electromagnetic torque, and the resultant of which is required, or we can say P required, which is the one that controls how your frequency would look like, because it's in direct relation with your mass of the system in proportion to how your frequency would behave. So this equation is being introduced into this control strategy, and due to this, what really happens is this, what really happens is this AC to DC converter, which is your part of your VSG or your virtual synchronous generator, is configured in such a way that helps you in overcoming your lack of inertia in the system. Let's talk about how this comes into play in simulation side. So they took two case studies where they disconnected solar PV panels. So when you disconnect solar PV panels, there would be drop of frequency because your power, real power in the system would go down. And they have taken a second case study where they introduced an induction motor load. Since an induction motor load is taken, it will take into some account for your some power uh, to help produce the right amount of torque required for your load, right? So let's talk about the disconnection of solar PV panels. So when you disconnect at this instant, at this, so you disconnected at this instant, and your frequency starts going down, right? And what you really want to do is you want to control this frequency, and this frequency could only be controlled. I mean, the decay could should be controlled first. It's not like the whole frequency's output would be controlled, but since it's a virtual generator, it would try and mimic power of your synchronous generator. So you can see that. Where did it go? Oh. So you can see that. So it went down to -1 hertz, right? So 50 hertz minus 1 is 49 hertz. And at the same time, your virtual synchronous generator kicked in and introduced power into the system. So, sorry. Hmm. So what really it does is it introduces power so that your frequency doesn't go beyond a threshold, which would cause devastating effect to your system. And in the second case, they introduced an induction motor load. So you can see the frequency was stable. And after some time, when they introduced it, it went down. And at the same time, your VSG kicked in. So what they wanted to check was, let's say they developed a control strategy for their controller. Now, what exactly would it be used for? How exactly would it be used by your um, in real time by your system, so that it's able to produce desired output, that is control of frequency. Just because you don't have inertia doesn't mean that your system should suffer from frequencies deprivation, right? Let me remember, why do I have this? I discussed case study 1, then I discussed case study 2. Hmm. Okay, so this was the conclusion of this demonstration. But since what you are doing is you are currently incorporating a, so let's talk about the challenges that you can face in such type of studies. So it's a stability analysis, right? You're studying stability. It's like how will your transient uh, how will your transients look like or behave like if this condition arises in your system. Now there are some challenges that are potentially uh, that can plague your system, so it won't be able to produce these requisite or required output. So the first is you need to have a proper modeling. So just so all of your equipments, all of your components that are in there for stability analysis, they should be properly modeled. Um, so so we all know, right? If they need to be properly modeled, right? But what can be the issues? So the issues can be, one, you may inadvertently employ an average model of your PV's converters. So if you have a PV, the converters. So what exactly do they do is they employ average modeling. So this average modeling averages out your responses over a particular period of time. You don't want that, right? So what you want to do is you want to decrease the small step size. If you decrease the step size small enough, the average even if you do average modeling, the output won't have a, if the step size is small, your output would mimic your transient requirement, right? Let's say that you had something like this, right? I would just make sure that this drawings are correct. Hmm. So let's say there are 10, 6, 4, 7, 7, 1, 2, 9, 5, and 2. So you had these units, and these are equally spaced, that is 1 second. So all of this is how much? 6, right? Now if you average it out over a 6 period, what would happen is the average would come out to be 16, 20, 29, and 36. Oh, nice. 20, 29, and 36, yes. So the average is what? 6. So your average came out to be 6 for a whole period. But if say, let's say you do it for 2 periods at a time. So if you do, the average for the first unit would be 8, and for the next two would be 9, 4, 6.5, and for the next two would be 7, 3.5, right? So it should be 3.5. So you can see that if you take a small step size, you would be able to mimic your exactly how your signal is behaving in time domain. So that is precisely how you should be modeling your converters with a smaller step size. That is something that you can configure in your RSCAD software. Next, the other thing that could happen is that for voltage support, you need capacitor banks. So let's say that you modeled everything correctly, but still what you're getting is something missing in your distribution system, right? You may have capacitor banks, but that is something that you wouldn't have modeled. Or let's say that is something that is required as well. So you need to be able to be conversed with how your system would react by introducing certain components, as well as by looking how they exactly behave in so you know how they exactly behave as well, so that you are able to overcome the challenge of voltage support in case you are trying to model how your frequency would look like. So modeling equipment. So third is your PI controller. Now when you use two or more racks in your RTDS, now you connect it using a transformer in your RSCAD module. Now I know you all don't have expertise in it, but believe me when I say this, when you use two racks, what are racks? So this is a rack. So this is a rack 1, rack 2, and rack 3, rack 4, rack 5, rack 6. So what you're doing is when you need more pins. So what you do is you create two subsystems which are interconnected between these two. And in that subsystem, how you do is you have a transformer in place in your RSCAD module. Now, let's say that you are doing that, but you use the PI controller and your converter looks exactly the same in your two different subsystems. Even though your converter looks exactly the same for the same power, for same stuff, the the PI controller used may not make sense. Why? Because due to the transformer in between your two subsystems. So your PI controller also needs to be manually changed, even if the converters are same. So that is something that you need to check. So there are other stuff as well. Your filter design, your filters should be such that resonant or resonance conditions don't arise or something. So you have to be conversant with these power devices so that you can have a appropriate or a well enough PHIL connect implementation of your system. So this is something that the instructor talked about, and I hope that you have expertise in RTDS or real-time simulators. I mean, I don't have a top-notch expertise, but I know certain stuff because I had a course during my first one here. Okay, the next thing that okay, so The next thing that the instructor discussed was peak energy management using battery energy storage system. So you all know, right? We have huge PV installations right now. The government is also focusing on PV installations everywhere. And even though the clean energy is something that they want to target, but due to the rise of this intermittent resources, what's really happening is that there are several operational challenges that are coming into picture, and these pose threat to your power system. Apart from that, there are mobile loads. So what are mobile loads? That loads that can be move in between different nodes, right? Let's say your EVs. You can charge at one node, then charge at another node. So these are mobile loads, and you don't know when these loads could come at which place. So it makes the job of your DSOs or your distribution system operators job to forecast the amount of power required for your distribution system even tough. So for this, what really you want is you want to have certain storage uh, um, storage systems in place in your distribution system so that you can take power from them and give them as and when required, so that your distribution system remains threat free even though there are a lot of intermittent resources in place. So in this, what really wanted to discuss was that, let's say that you have PV generation during the daytime when the loads are less. So let's say yeah, when the loads are less, you have a surplus of energy available to you. And when you have a surplus of energy, what you do is you feed it back to the grid. Now, if the grid already has power, why would it require power, right? I mean, it would surely require power for flexible operation, but think of it in a perspective. Let's say that the grid has enough power available at its own end. So when you feed this power back to the system, there is a surplus of energy. And instead of giving this energy back to this grid, which sometimes won't require this much amount of energy, what you can do is you can have BESS available at your storage side only so that you can store this energy in your systems. So through this study, what they wanted to propose was, let's say that in IIT Roorkee, they have this distribution network. They have a lot of solar power available. This is all solar, right? So everything in red is solar. So what really happens is that during chances when, let's say, it's a holiday on Thursday, right? Recently there was a holiday on Thursday due to Eid, and students went out. They went out to roam around, and there were no loads available in the campus. So the campus experienced a surplus amount of energy due to the installation of these resources, right? So what they want is they want to use BSS to be able to soak in this power when the PVs have surplus available. And so PVs, if they, let's say, in ADNs or active distribution networks, so ADNs are active distribution networks. If generation from PV, PGen, PV is greater than P load, a condition of overvoltage arises, and if PGen is less than PV, or sorry, P load, a condition of undervoltage arises. To protect from this, your batteries could be used, which give you the power of voltage control, managing the intermittent and stochastic power generation, and other stuff, right? So for this, what they did was they simulated the whole network on RS-CAD, and they checked for voltage variations at each bus. So all of these, there are buses, or nodes, 1, 2, 3, 4, 5. All of these are nodes, right? So at these nodes, they check how the voltage is varying due to this large influx of PV power, right, at the distribution side. After this, what they checked was there was a large voltage variation, but now they wanted to curb it. And curb it how? By optimally placing batteries. And what they did was they after getting the required output from the RS card, at what places the inertia, sorry, at what places the voltage variation was quite high. What they did was they tried and solve an optimization problem on an mixed integer linear programming objective. Sorry, function. So what exactly this is? A mixed integer linear programming. In mixed integer linear programming, you have a bunch of linear and non-linear. You have only linear functions, and mixed integer tells that you have integer as well as continuous variables. Right. So, and binary, it can have a binary as well. That's why it's called mixed. So you have this mixed integer linear programming formulation of your problem. And what you did was you checked where exactly the optimal placement of your BSS would make sense. So what exactly is so you had an objective function which was minimize voltage variations, right? And for that you had constraints such that voltage is in some limit, and then you had your sorry, this would also include some minimum of voltage variation, and what you want is negative power from BSS, some objective formulation, some function of your PBS, right? And you had your constraints related to BESS as well, right? So this kind of problem formulation, I don't know exact problem. They didn't talk about this or exact problem in their demonstration, but and I can't configure a problem right here and right now, right? It it takes time to formulate an objective function which is suitable for your implementation. So what they did was they checked where exactly the battery power and how much amount of battery power would be required, and they got this number that at bus number 1, 2, 7, and 15, they require this amount of battery with this amount of energy and power. And after that, what they did was they simulated this infrastructure as well. So they installed the batteries at these locations, and then again they did PHIL simulation, and they found out that the voltages were within the range. So this is what is the benefit of your PHIL, right? Instead of just going in the field installing components here and there without a worry of how your system would react to unconstrained or violating different situations, you can simulate it on an RTDS platform or a real time simulator, so that all of your worries uh, could be vanished before you install it on a field pilot or a real life scenario. So before moving on to conclusions of the uh, you say I won't say subject. I mean, I just have a few conclusions that I want to give and some projects that are being undertaken but at IIT Kanpur. But before that, any doubts until now for this class? Anything that I forgot discussing that you want me to discuss? Anyone? Hmm? No one. Okay, I have a chat. Okay, okay, from Nitin. No questions, right? So you must have seen that last few weeks the lectures are not that conceptually heavy. I mean, they are just demonstrating stuff, and and I also don't have a perfect explanation for what kind of systems they are using, because I didn't simulate any of that. I didn't demonstrate any of that, right? So they have first-hand experience, and they would be better able to tell you how this thing is coming. But it's a demonstration, right? I don't think it's completely relevant to your um, course at hand as well. It's just that they want you to be familiar with how you can have real-time simulations done, so that if anything that you're proposing for distribution networks for today, that can be um, checked before being deployed at real world. So any doubts in this class? I mean, no doubts. Let's move ahead. So, so all of these things that we discussed the whole 12 weeks. So what really we wanted to convey was, or the instructor really, what really the instructors wanted to convey was that the due to the um, due to the evolution of these technologies, your systems needs upgradation as well, right? Let's say that you don't use a keypad phone nowadays, right? You use a touchscreen phone. So similarly, if you have a, a, a wide range of what can I say? If you have a wide array of technology available at your hand, you will use them for the benefit of your our system, right? And that's exactly what's it being used in nowadays. Earlier, they used to be RTUs, right? These uh, remote telemetry units. Now we have replaced them with phasor measurement units. Why is that? Is because we want to be able to um, we want things to change with time, and we want things to uh, be monitored in a better way. The RTUs, even though they gave their time scale was very less, they gave signals in 2 to 3 seconds, while PMU could give you uh, in milliseconds to seconds range. So that is what you want, right? So you want your system to upgrade so that whatever you're using now could be made better in future. And smart grids are being evolved in the same rate. Now you have here, so who would have thought distribution system which consisted of only loads will now have generations in the form of rooftop solar PVs, your EVs, electric vehicles. I mean, long back, this Edison fought for DC, right? He fought for DC, but he was defeated by these AC guys. But now people see that AC has a lot of defects. I mean, still being used, it's still relevant because of low losses, uh, but due to skin effect, the corona, etc., it's not available in DC. So people are now valuing how DC would benefit them, and that's why these PVs, these EVs, etc., come up with the battery, right? So so now these DC based equipments are there in your distribution system, but now you want to manage them effectively, right? Let's say if everyone has EVs, let's say you wake up next day and all of you have EVs. So you what you would do is you would charge them at the night when you come home from your office. And if all of you do that, what will happen is your peak of your load will change. Earlier it was in evening. Sorry. Earlier it was in evening. Now it will be in night. So in night you don't have TVs. You don't have other generations available at your hand. So if the load curve would change like this, it would cause operational issues at your distribution system's end and how they behave. So that is something that you want to control, and it's by constantly adapting to these technological advancements. So similarly, smart grids in sorry, it's gone available, right? Hmm. So now what really happened? What really India wants it wants the smart grids to evolve. So for that, what they're doing is they want smart grids in smart cities. So they have established smart cities, right? So the place where I come from, Jammu, it's also a smart city. And what they have done is they have implemented smart meters at all of our homes. I also now don't have to pay for, so I don't pay electricity bills. I prepaid or prepay my electricity uh, beforehand or before the start of the month so that I can have electricity for the day. And if I don't pay, let's say if I forget paying sometimes, what really happens is that smart meter is equipped to cut off your electricity. And also I can view how my parents, they are the ones residing in my house, so at their house, so they how they are consuming this electricity, right? So earlier, I didn't used to think about it. The bill came, it was like 3,000, 4,000. I used to pay it. Now I see the usage 200 kilowatt hours in a day, right? 200 kilowatt hours is too much. It's pretty huge. So now what really happened is, due to smart meters, you are now taking charge of your electricity usage. You now think about it like, okay, my energy usage is quite high and it's not good. I should do something about it. And that's how people would become responsible as well. Then you want proliferation of electric vehicles. Government has introduced several subsidies, the same subsidies for your EVs, two-wheelers, three-wheelers, four-wheelers, etc., etc. They want electric vehicles to be available at all these, at most of these homes for clean energy, so that reliance on fossil fuel is less, etc., etc. Then they want efficient usage of existing sources. So let's say that you have, uh, let's say earlier, what really happened was, if it was a passive load, right? Your distribution system, with increase in loads, it would require to go into restructuring as well. So you would require to install new lines, new transmission equipment, so that you would meet the same load in 10 to 20 years from now. But with the proliferation of generation and distribution systems, what you can do is you can delay that. You can delay that investment. Why? Because you have generation available at your end, right? So you would want to use it. Then they want 40 gigawatt of rooftop PV by 2022. So this was for 2022, but it has still not been reached. So the government has revised this target again, and they have now set it for 40 GW for 2026. And as of 1st October 23, we have 11 gigawatt of RTPVs installed. So you can see that the number is quite less, 29 less, right? And we have 3 years to go. 2 years to go. Let's hope for the best. Then they have implemented three full-scale projects, each costing of about 258 crores. Then they want industry collaboration with ESCO model. So what exactly is ESCO model? In ESCO model, what you do is, you have land available at your end. You ask your energy supply, or your energy generating company to install a plant at your end and just pay you the amount that you have, what you say, the amount that you have agreed on your agreement. So this is what they want in through industry collaboration. And 35 million installation by 2019. So I hope this is of smart meters. I tried checking out in various documents. I don't know what exactly this objective was, but I hope it's for smart meters. And in IIT Kanpur, we recently received, I mean, not recently, in 2018, we received funding for establishment of an IIT Kanpur Smart City. And in this, what we wanted to do was, we wanted to have a smart city pilot project in the IIT Kanpur's campus. So we'll discuss about it. And for that, what we wanted was demonstration of future capabilities of smart cities. We wanted renewable energy integration by in the form of grid connected PVs. We want robust communication network for information exchange, advanced metering infrastructure, and home automation systems. And what we have done is, we have implemented SCADA, and we have also implemented rooftop solar at all of our hostels, at all of our departments, and at most of the residential houses as well. We also have storage supported grid connected hybrid inverters installed. So they are called hybrids because they are configured with the grid as well as with the storages. And we also have a smart grid center, SG center, which is used for control and monitoring of our whole scenario. So I've taken this SCADA overview from for our campus. So you can see we have a uh, 13 bus system here in place, and this is a very crude diagram. I mean, so in SCADA, what you really do is, you can have what kind of components to install at what place. So I mean, they didn't do a lot. They didn't do a good job in developing a good interface or an overview for this whole system, but it works for us. So the green lines is, it means that the whole system is in a discharge state. this purple line means that it's a 1415 volt line, 415 volt line, and the blue lines mean it's a 11 kV line. And at each substation, it's configured to either a hostels or different departments, and we have 13 buses available, and we can monitor the whole IIT Kanpur using this SCADA. So we can check which circuit breaker is open, which lines are in discharge state, etc., at all times. Now, in addition to this, uh, we also have uh, we recently concluded our US India collaborative for smart distribution systems with storage. So in this, this was a UISS project, which was a very expensive, I should say. I don't know what to call it, but it was a very big grant received from the Indo-US department. And in this, we had collaborators from US, which were in the form of Washington State Universities, MIT, West Virginia University, Texas A&M, and etc., and the various different industry partners as well. And at the Indian side, we have a uh, sorry, we had a we had collaboration from different IITs, five IITs, I guess, Bhubaneswar, Madras, Roorkee, and Delhi, and we had support from Terry and different entities which deal with power systems components. And in this project, I'll discuss what the objectives for IIT Kanpur was. The IIT Kanpur was the technical lead from the Indian side. So, if I don't know if you've heard of Dr. S.C. Srivastav, he was the technical lead of this whole project. And in this project, what really we wanted to develop was we wanted to develop three different kinds of pilots. One was a rural pilot, then a semi-urban pilot, and an urban pilot, in which we wanted to showcase that a smart distribution system with storage can be developed for a rural side, a semi-urban side, and an urban side. So for a rural side, we took a village called a Harnu village, which had hamlets of different villages. So in hamlets, I mean there are different smaller sections of people living in different parts of a whole village. And in both of these villages, what astonishing we found was that both of these were unelectrified. That means none of them had uh, access to electricity. So I would like you to go to UISS in your free time, not now. Go through this lecture first and then go to this uiss.org. There you can find material pertaining to everything. And we have a YouTube channel as well. There we have recently uploaded 4 weeks ago. I mean, not us, IIT Kanpur people have recently uploaded a video in which they took into account of various different beneficiaries of this project, and I would love for you to check it out. You will see how this whole pilot helped the people over there. So what we wanted to do was we wanted to so there was no transformers and the wires etc. were not that were there provided by DVVNL, which is a distribution utility here in UP. They were not reliable, so the transformers were not reliable. They could go off at any time. So what we wanted to do was for these 700 people, there were only 700 people. We wanted to develop a pilot which ensured 24x7 power availability. So for that, what we did was we installed first a 63 kilovolt ampere transformer, and we also installed a 70 kilowatt this solar PV panel. Yeah, just a second. Sorry. So so the solar panel was installed at Chhaba, Nevada village hamlet, and the other one was at Baragadia Purva, Baragdia Purva. Both of them are part of Harnu village, which is around 45 kilometer from IIT Kanpur. And you can see that both of them had the same transformer, same no solar panels, One was of 70 kilowatt peak and the other was 30 kilowatt. And we had lithium ion battery energy storage system, both 50 kilowatt, 100 kilowatt hour energy, and a hybrid inverter. And both of these hamlets were interconnected with an AC-DC AC converter so that we can have power exchange between both of these hamlets as well. And in addition to that, we had a hybrid biomass plant. Now, this biomass plant, what exactly the need was that we found the teachers or the professors found out that the investigators found out that there's a lot of cow dung or the cattle feed material available at the both of these villages. So what we wanted them to do was feed in this biomass because it's a biochemical feed to this biomass plant so that a 30 kilowatt of that could also be maintained. And based on that, we were able to successfully deliver power 24/7 for both of these villages or hamlets of this village. And the challenge that the investigators faced was first, they wanted to sensitize the local community. So you want them to be able to feed in this biomass to this hybrid biomass plant, right? It can only be done if you sensitize them of the opportunities that they could get from 24/7 availability of electricity. So sensitizing was something that needed to be discussed, right? And the other thing was since it was the land, right? It was the village's land. So approval for the land was also something which was tough. So we overcame this challenge and we were able to deliver this rural field pilot project as well. Next thing was a semi-urban field pilot. In a semi-urban field pilot, what we wanted to do was we wanted to have in our IIT Kanpur, we have residential houses for professors. And in these houses, we took 30 houses from some lanes, lane 32 and 33. And in these 30 houses, we installed smart meters with solar PV rooftop and both of them were integrated with both of these lanes were integrated with the lithium ion BESS as well, and also an EV charging station. So this was a semi-urban field pilot that we were able to demonstrate as well. So this was also taken up in IIT Kanpur. So I forgot telling you, this was from 2017 to 2023. Right. So this was the semi-urban field pilot in IIT Kanpur, and the other was, so you can see, right, we were discussing these things as well, how to connect, how this hybrid inverter. So we were figuring out the PHIL implementation of all of this. Now, after this PHIL implementation, what's the next step? It's the field pilot demonstration. So that is what we were able to figure out. The next thing was an urban field pilot. In an urban field pilot, you want to have uh, um, electricity available for critical loads, right? So there are critical loads available at your apartments as well. So you can see that earlier this diesel generator in the substation, this 5 by 10. So we can see the 5 by 10, I guess. Let me search for it. This substation was feeding power to the faculty apartments in IIT Kanpur. What we did was we installed solar PV rooftop and we installed a lithium ion battery energy storage system which worked with the hybrid inverter, smart hybrid inverter. And the function of this BESS was to power critical loads such as common area lighting and the lift load of the apartments. So if someone lives on the top floor, seventh floor, right? So if there is no electricity, they won't go through the, if some emergency takes place, they won't take the staircase, right? So for that, lifts were taken in as a critical load, and they were able to demonstrate this as well. And all of these houses, etc., were configured with a bidirectional power flow and smart meter. So you can see that smart grids have have the ability or can be used to make sure that all of your system could be empowered even in case of adversity. And that is something that we were able to showcase from this whole project. And this is just from the IIT Kanpur sides. Projects were taken from the IIT Delhi sides and Madras, etc., etc., and from the US side as well. So you are free to check this link, uiss.org, to all the thematics and the outcomes from this whole project. There was one white paper released as well, which was transforming Indian power sector distribution system operators. So it's a white paper which tells us how distribution system operators would come into being, what are the various regulatory practices which would be involved, what are the technical aspects of it, etc., etc. So you're welcome to read that as well. If someone wants a copy, I can send them. I think it's available freely on the website as well, so they can check. And then they'll be able to appreciate how a DSO model should look like, right? So your DSO should be fair. Your DSO should be empowered so that its forecast is something that is able to get power cheaply from day ahead market without relying much on real time market as well. So all of this and the other regulatory practices were discussed in that white paper. So that was it. That was it for the whole course. So we'll discuss MCQs, but this was it for the whole 12-week course. So if anyone has doubts, please come forward. I'll give you 4 minutes to come forward, and after that we'll discuss questions. So I wanted to discuss this few aspects because conclusion from a perspective of from their perspective wasn't making sense to me. So what I wanted to do was I wanted to show you how IIT Kanpur was making initiatives or taking initiatives to ensure the upliftment of the smart grid objectives of India. So any questions, anyone? We only have two students, so I would appreciate if you have questions. Dharani, no question today?
Hi, sir.
Hi, hi.
Sir, I have small doubt. Actually, I started to type in chat. Okay, I will ask.
Mm-hmm.
Um,
Mm-hmm.
in AC, according to the swing equation, we can say relation between frequency and power demand. Like if P generation is greater than P demand, like frequency will be increases like that. In DC, is there any reason why if P generation is greater than P load, over voltage it will come like that?
Okay, so what really happens is, Dharani, so in AC side, so I discussed this, but I will discuss this again. I discussed this quite a few backs, but in a few days back when we were discussing droop equation. So in AC, your droop equation is directly relevant on your delta and P and your mod of V and Q, right? So we have P delta droop equations and you have QV droop equations, right? These are
Yes.
for AC. These are for AC. Now in DC side, the only thing that is available is power, your real power. So so in AC side, what we really did was we took a few assumptions. The assumptions were of that the R by X ratio would be very less, right? And this R by X ratio resulted in the decoupling of both of these to the form that the real power would only depend on frequency and the reactive power would only depend on voltage magnitude. This was due to rho R by X ratio, which resulted decoupled equations. Now, in DC side, you don't have Q, you don't have frequency. The only thing you have is power, and the only thing you have is voltage magnitude, right? So, and you don't have impedances. You only have you're only responsible for resistances. So the only thing that is interfering in your voltage equation would be the drop across that resistance, right? So your real power would indirectly be dependent on your voltage magnitude. Why? Because in DC side there is no concept of QF or QV relation. So your DC side, the droop equation looks like this. But it won't be fair to say that P is only dependent on this. This P delta droop comes into fact that we took into some account some assumptions which are only possible for AC side. So that's why the droop equations were the droop equations which show the uncanny resemblance on power and frequency and Q and V is because we took into account these assumptions which are only valid in AC side. Since we don't have an AC side anymore, we have a DC side where there is no Q, there's no F, we only have P and V. The PV relation would hold true in all cases. That's why we took into account this over voltage and under voltage.
Yeah, sir, I got
Hmm.
it. But if
Hmm.
P generation is greater than P demand, you are saying like we are saying like over voltage. If
Hmm.
P generation is less than P demand, we are saying under voltage. Why not it
Hmm.
is reverse? Like if P demand is greater than P
Okay.
generation,
Hmm.
that is
So let's okay. Let me think about it in this way. Okay, so let's say that you have four. Let me think of something. So you have 4 kilowatt of load available at your end, right? And I am asking you, and you want 4 kilowatt of uh, generation to be able to have a voltage which is 230 volt. Right? Not call it 230 volt, let's call it 48 volt DC side. But let's say if I'm supplying you with the power which is 8 kilowatt, the drop would be less and the power available at your end would be high, right? But you won't be using that whole power. You would only be using 4 kilowatt out of that. Now the remaining part would ensure that due to this drop, the voltage doesn't come out to be significantly low because you are not withdrawing the whole power. You still have the power available at your end. So if you have this power available at your end, your voltage would trend to go up because something needs to consume that, right? So your voltage. So let's talk about it this way. Let's say you have 20 nuts, right? And you use only 10 nuts to get satisfied. But if you are 20, if you want your appetite to be satisfied, you will use all of those 20 nuts. So it's like that only, right? If you have availability, if you have abundance of power available at your end, the voltage tends to rise. It's because it's being consumed less in your overall this what to say this the drop that you're taking in. I can also show you from this end. Let's say that P is equals to VI, right? So I is something that is responsible for your load. So if your P increases, your VI needs to remain constant. So but your load won't increase because your load is something 4 kilowatt, it will stay constant. But so to keep this equation balanced, to keep P is equals to VI, your voltage will tend to rise. So that's why this happens, because something needs to account for that excess of energy, right? So your voltage starts increasing. That's what happens in your DC side. So you have abundance of power, load is less, the voltage will rise to keep the VI equal to that power available. Any
yes,
you
got clear.
got yeah, I think I should have explained it through this. I mean, I was trying to explain the same thing, but I should have drawn. Any other question? Yeah, I'm still learning, right? I'm learning to teach. So I think I should use the whiteboard available at my hand in any case when I have. Yeah. Any other doubt?
No, sir, that's it.
That's it. So this is how it comes into being, right? And remember that I told you for distribution system you don't have R by X ratio very high. So what? No, so sorry, R by X ratio very low. So what you really do is your power is dependent on your voltage magnitude as well, because this group won't make sense because the assumptions no longer hold true. So your power is also dependent on your voltage as well as on your frequency. So the same thing happens in your DC side as well. So let's move on to questions then, since there are no questions. Very easy questions this time. So let's start with the first question. What are the working modes of DC microgrids? Hmm. So you can have grid connected, you can have islanded when there is no grid, and you can have an autonomous. That is something that works on its own. That is what was there in Harnu village. So all of the above is a correct answer. Second, match the following. Take your time. These are just what it's called, abbreviations in their expressions. So let me know if someone did it. See, so okay, so DFIG is your doubly fed induction generator. So 5. RTDS is your real-time device simulator. Real-time digital simulator, but okay. 3. Then PHIL is your power hardware in loop. And then you have FPGA, which is, oh, real-time digital simulator is there. 6. And you have FPGA, which is field programmable gate arrays. Then you have 5, which is hardware in loop. Oh, so they had 6. I thought they miswrote this. Okay, so the answer is 56412. 56412. Yes, C. C is the correct answer. Let's move on. Next question, B. So we have to identify correct statements out of the 3 statements or 4 statements. So okay, someone said B. So we have maximum solar power injection during off-peak load hours may result in under voltage conditions. Off-peak load hours, if we have, no, this is wrong. Then we have peak load hours where later on may result in under voltage. This is true. So we got our answer, right? And reverse power flow is not possible, false, and all of it. So fourth, battery energy storage system has been proven to be an effective solution, but see, I don't know. So reverse power flow is possible in ADNs, right? So you have, so this is what I wanted to show you. So your AC can give power to your grid, but in cases when your grid doesn't require power, you can feed it to a BESS. That's what I wanted to tell. So reverse power flow is there in ADN. That's why we have the, yeah, bidirectional. Yes. Yeah, reverse power flow is bidirectional power flow. It's reverse of the original power flow that is supposed to. Fourth, battery energy storage system has been proven to be an effective solution for dash. T. Yes, we can do it for voltage control, flattening of load curve, reduction of power losses. So all of the above is correct. So, fifth, what are smart grid R&D areas under ICT and cybersecurity? ICT is information and communications technology. So, you know what's the correct answer? D. Okay. Seamless grid operation involving transmission and distribution system operators. Reliable wired. So this doesn't come into smart grid R&D areas under ICT and cybersecurity. And reliable wired and wireless communication technologies, this does come. And then coordination and control of multiple converters, this doesn't. So all of the above is wrong answer, no? So ICT only covers the communication part and the cybersecurity part. It doesn't it is not concerned with how your converters control multiple converters are controlled, or how your distribution system operator and transmission system operators are involved. So this I guess they have taken from last class of the 12th of this week's lecture. So just skim through the different smart grid R&D areas, you will be able to find that B is the correct answer.
Sir, if they ask
Mhm.
only for the smart grid R&D areas, means all of the above will be correct.
Yeah. Under ICT and cybersecurity, only the B is correct.
Okay, okay,
Hmm.
sir.
Yeah. Sixth question: what are primary goals of Indian smart grid pilot projects and distribution systems? So, what do we want to have in Indian smart grid pilot project? Yes, not maybe, it's D. We want to incorporate AMI. Sorry. We want outage management systems so that once an outage happens, you want your critical loads to be powered. Your peak load management should be there. So all of the above is the correct answer. Now, what are the main features of DC microgrid? So when someone talks about features, it's always D. Yes. You want grid support, you want flexibility, you want stability, you want flexibility and reliability. So all of the above is the correct answer. Eighth, the excess load demand in ADN results in. So voltage sag means your voltage starts going down, and reverse power flow is that it flows back to the main grid. So if you have more load demand in ADN, what would happen? A. Okay. So let's talk about this. That you have a distribution system. Okay, you have a distribution system. The load is there, and you are taking power from some utility. Some PVs are there. So when you have excess power available, when your load increases, your PV would feed this, right? It won't feed power back to the grid. And if the load increases, your voltage will sag because the would be less for uh, generation may be less because the load has suddenly increased too much. So voltage goes down only, and there is no reverse power flow because you wouldn't want your power to go back to the grid, right? You want your power to be consumed by the increase in load present in your system. So the answer is C, voltage sag only. Did you get it, Dharini? Why A won't be the correct answer?
Yes, sir. Like, but if
Hmm.
active distribution network means we should imagine it is like it is not related to AC, it is only related to DC, like PV and BESS.
Hmm. No, but tell me one thing, Dharani. See, the questions can be dubious. They can have different meanings as well. But if you think about it, if you have an ADN, let's say if IIT Kanpur is the case, not IIT Kanpur, let's say that you have a distribution system at your place. So if you have PVs installed and there is a sudden rise in load, and this excess load demand means that you are not able to supply this solely from your AC utility side. So if you're not able to greater than your utility side generating power. So if it's greater than this, your power coming from your PVs or BESS would be directed to your system, to your load. And reverse power flow means that it is being sent back to the utility. So you won't send it back to the utility, right? You would want that power to be consumed by your load at your distribution system end only. So that is where only voltage sag will take place, not the reverse power flow. The power won't be fed back to the grid.
Yeah, yes, sir.
Hmm. So ninth, over voltage in ADN signifies what?
Option A.
Okay. Why can't it
Both
be
A.
lightly? Yeah. Yes, yes. So C is the correct answer. So it can be due to high power injection and lightly loaded condition. So 10. So last this is from last week. I don't know why. So at what layer of control does power flow control fall into? Primary, secondary, tertiary, or zero level? So always remember zero, primary, secondary, and tertiary. The time, sorry, the fastness decreases. So power flow control is, do you want it to be fast? Sorry, is it a fast control, fast acting control? What do you think?
DC microgrid means it will be a fast control only. I think so.
No. So let's talk about this. So,
Yeah.
so at the zero level, you first want your grid tied inverter variables to be controlled. Then in primary, you want automatic load sharing or grid support. In the third, you want your microgrid synchronization and voltage and frequency control. And in the fourth layer, which is the tertiary layer, you will want your power flow control or optimization control because it is slow acting control. So based on how your control layers dynamics behave, the time taken by them, your uh, your layer of control is designed. And the power flow control of a DC microgrid usually falls in tertiary because the control is the dynamics to control it is very slow, and for the rest of them, they are very quick. So this we discussed last week, I guess, and then we ended there. Yes.
Okay.
So any doubt up until this point?
I think one question I seen like in the last week I think so. Transmission system has R by X ratio. Transmission system and distribution system.
Okay. Dharani. See, this was last week only, I remember. So, see, when I talk about R by X ratio, it means resistance upon reactance, right?
Yes.
I can also talk about reactance upon resistance,
Ah, I got this
right?
explanation, but why uh, transmission system has higher low and why distribution system has low or high something that.
You want to? Oh, yes, yes. So, okay, yeah, that can be very easily answered. So, it's dependent on certain facts. So, if you are conversant with how transmission systems wires are and how distribution system wires are. So in transmission side, the wires are equally spaced, so you can control their spacing, and the power that they usually transmit is at a very higher value, right? So the current. So why do we transform that at a very high power, high voltage value? Sorry, I'm saying power. Higher voltage value is that the current inside the lines would be very less. So if the currents are very less, the drops would be very less. If the drop, that is the I square R losses, are very less, your dependence or your resistance coming into the dynamics of your transmission components would be very less. But in the distribution side, this is not the case. In distribution side, you have multiple phases. There are single phases, double phases, three phases. You have different distribution system transformers, control components, etc., etc. And the amount of power is less. And the conductors and their sizing and their spacing, it's usually narrow. Due to which, what really happens is there is an increase in the resistance of your wires, which come into the dynamics of your control algorithms. And this control algorithms then this this takes into account that the distribution system usually have a high R by X ratio, which is not present in the transmission side due to the fact that dynamics are easily controlled. So it's dependent on the wires, and it's dependent on the amount of current being transported in your wires. Due to the high voltage level and the width of the wire and the spacing of the wire, your resistance doesn't come into picture much. But in distribution side, it does because you have shorter length of wires, and You have multiple wires in the same beam going from one direction to the other. So there's an accumulation of resistance in that case. So there are multiple reasons why the resistance component is much higher in distribution side. That's why in distribution side now, when we do dist flow, we are only uh, concerned with the voltage level, not with the frequency and etc. Because we know frequency we can keep it constant because X is very small. The resistance which actually causes the drop in the voltage is very high. So hence we take into account the R by X ratio to be very high for distribution system. Now you got me?
Yeah, yes, sir. Got it.
So it's because of wires, it's because of the amount of power being transported, the current, etc., etc. And the distribution side, usually you would see that resistances are very high. And due to the resistances being high, the voltage drop will be very high. So there's no perfectly balanced way to tell you that why R by X ratio would come into play. I mean, if you would have searched it on internet as well, right? You would have gotten some saying the wires are smaller and skin effect is pronounced, or they would have said the length of the wires is small. I mean, there are different reasons that result in the accumulation of a higher resistance in the distribution system.
Yeah,
So
okay,
usually
sir.
we say that it's very high. Yeah, so this was for the whole 12 week. So we covered everything for smart grids. At least I think so that the instructor has covered everything. So I hope you had fun. I mean, your exams are very close, so I hope you are practicing for that as well. And if you have any doubts, you can always reach out to me in the YouTube comment section, and I would be happy to answer that. And I hope you had fun in this 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 course. I mean, it was a nice teaching experience for me as well. So did you have fun?
Yeah, yes, sir.
Any feedback?
Uh, Actually, starting, I thought that I didn't got time to watch these videos, how it will be like. I thought whether I can spend time or not. But when I listened first time, after that I continuously started to listen without missing. Actually, I thought like I
So
should first listen.
y- yeah, that's why what I do na these lecture doubt clearing sessions na usually what really happens is they are scheduled. They can be scheduled any day from Monday to Sunday. So I usually keep them on Saturday and Sundays is because I know there are a lot of working professionals who would take the course. So taking it on Saturday and Sunday would that helps me as well. Saturdays and Sundays are holidays, so I can just devote time for teaching. But my general notion is that Saturdays are something that people can invest in as well. So it's like you can watch the whole 5 lectures from morning to afternoon, and then evening you can take this class so that you can be up to date with everything that is being covered in the course so far. So that's the purely my reason of why I took the evening class schedule. I mean, it doesn't suit me. I'll tell you because evenings I'm really tired and I just want to end the lecture and sleep. But uh, but that's something that I developed habit of last week. Last time as well, I took fundamentals of electrical engineering, and I took evening course schedule as well. But so
Okay.
it was a very nice experience for me. I hope it was for you as well, and that you do well in your exam. When is your exam?
I think I seen as April 26, but till hall tickets are not released. Till date is also.
So you have I guess 2 weeks, 13 days. Yeah,
Yeah.
so best of luck. I mean, there's only one student left. They started, it happens. So a lot of people join and then they start leaving one by one. Yeah, so I
Yeah.
hope you have a very nice experience. You had a very nice experience and that you score well in your exam. Do let me know how well you scored. I mean, I won't have a way of knowing that, but I hope that you score well.
Yeah, yes, sir. Even I started listening your videos from week one. When
Hmm.
I listened to the NPTEL videos, I thought the data is given up to 2016, 2017. In week feedback, also I written like if we got like this sessions means up to 2022 or 2023 data, it will be good. Now in India,
Hmm.
PV generation and base come into picture, that is increased, but that videos are like up to 2016 they are talking. even the
Yes, whenever the data was there in my earlier slides as well, I tried including the data in what in the real time scenario. So let's say if the data was required for, so I tried uploading data for up till 2023. So I made
yeah
sure to check if the data is up to date or not. But yeah, see, it's an NPTEL lecture, right? So an instructor doesn't have a lot of time to go on and update the lecture material every time. So what they do is they rerun the course, but it's our responsibility to make sure that when we give the lecture, we make sure that the data is up to date. So that's something that I planned on doing. So and it's helpful for you, I guess, right?
yeah
So
yes
you
sir.
if you get real time data for a working professional, it's very
Mm-hmm.
beneficial. Hmm. Yeah. So let's hope that you have a nice exam, you score well, and let me know how good you scored. And if you have any doubts, you can always reach out to me. Right.
Yeah,
So I'll I would like to bring this session to a close now. So so best of luck, Dharini. Best of luck to everyone who watches this on YouTube. Feel free to reach out to me on YouTube comment section. I would be
yeah.
happy to help. Thank you. Thank you. Bye.
Thank you so much. Bye.
Bye.